Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. So a while ago I bought some step-down DC-DC converters. Very cheap one, about $1 and a few cents, or €1 and a few cents, depending on how you would like to express prices. And I didn't do anything with them until now, and now I decided I should test them and see how good they work and what are their performances. Now I'm gonna show you a local store from my country, but it doesn't really matter. You can find these all over the internet, in all sorts of places. They might come with the name MP1584EN or maybe you will have some with the integrated MP2307DN, or maybe you will have MP2307DN. It doesn't really matter. These are very cheap DC-DC step-down converter, or buck converters as some people might call them. They're very small. They are the size of a finger or something like that, and not really an entire finger length, just the size of a fingertip. And electrically speaking, they are very simple. They have an integrated circuit that has almost everything, an external coil, inductor, and a trimming potentiometer, and a few other components, mostly capacitors and resistors, and that's it. That's the whole power supply. Now, needless to say, since they are so cheap, two things can happen. One, we might be very tempted to buy them and buy not just one or two pieces, but buy multiple pieces of them. And two, we kind of need to ask ourselves really how good they are, because if the final price is about $1, $1.50, then yeah, or the equivalent of $1, $1.50, and that price, we must be aware that that price contains also the excess money that the distributor wants, you know, because he wants to have some profit by selling these products, right? And these products are not manufactured in the countries where we are, right? They are manufactured in China, probably. So there are some import fees, import taxes involved. So if the final price ends up being $1 or $1.50, that kind of raises a question mark, if not an exclamation mark, regarding their quality. And this is what I've done today, and what I've wanted to test, basically. Because if we just read the characteristics, the specifications, they sound very good, except the fact that they are not true, and at least not entirely. Okay, so at least this online shop says that these converters can take between 4.5 and 28 volts on the input. The output voltage would be adjustable between 0.8 and 20 volts, and it has a maximum output current of 3 amps. It doesn't really specify whether it's 3 amps for short amounts of time or 3 amps continuously. We will see in a moment that it's not 3 amps continuously at all. It also tells us that it has a maximum efficiency of 92%, which sounds good, and well, yes, in reality it is close to 92%. A working frequency, or a switching frequency of 1 megahertz, which is not true, but it doesn't really matter all that much, and a ripple voltage of only 30 millivolts, which is false. But we'll get to that, okay? So my desire was to test a couple of these and see what they're made of, basically, see if these specifications are right or not. So, like I said, I have an MP1584EN. Well, I have several boards with this particular IC. And I also have some other boards with MP2307DN. Electronically speaking, they are very, very similar, pretty much the same components, more or less. And also pretty much the same physical size. I don't remember actually buying different kinds of boards, but anyway, this is what I got. I bought them many months ago, so I don't fully remember, but it doesn't matter. So I've put them both to the test, and from MP1584EN I've actually tested 3 of them, because I have 4 of them in total. I've actually tested 3 of them just to make sure that the results are not wrong, because I ended up having a broken board. Anyway, we will start with MP2307DN, because this board performs the best, and we don't really have problems now with it. Now, before getting into the results, let me explain to you what I've done, so that you can understand, and so that you can also apply this test to any other DC-DC converter that you wish to test, or really in general any other power supply that you would like to test. So with the DC-DC converter, we're supposed to provide an input power source, which needs to be of a higher voltage than the voltage that we want to have on the output. And on the output we have a certain voltage, sometimes fixed, some other times variable. And of course, in the end, we connect that voltage to a load, which in this circuit I've symbolized it with a simple resistor. Okay. In my tests, I've actually used an electronic load that I've built myself a while ago. But to simplify things on the schematic is a simple resistor. And there are basically a few things that we want to take a look at. We need an ampermeter and a voltmeter on the input to measure the current going into the board that we are testing, and also the voltage that board will receive. And also we will need a voltmeter and an ampermeter on the output of the board to measure the output voltage and the output current going into the load. In order to visualize the output ripple, we will also need an oscilloscope connected to the output, basically in parallel with the voltmeter. And because most likely the board will heat up when working with higher currents, we will probably want to monitor the temperature with a thermometer somehow. So this is basically what I've done, except in my case I didn't put a voltmeter on the input at all, because I use reliable power sources on the input. I fed these boards that I've tested with 10 volts on the input, and I am 100% sure of that voltage, so I didn't need it to measure it with a with a dedicated voltmeter. Okay, so in my case I have 10 volts on the input. The power sources can give a maximum of 10 amps, which is more than enough for our test. We will not get anywhere near 10 volts on the input, and the boards have been adjusted to output 5 volts, or a voltage as close as possible to 5 volts on the output. Okay, so this has been the setup, and this is the way I have tested these DC-DC converters. Okay, and now let me show you the results, starting from the happy results that I've got with the board having MP2307DN integrated circuit. I have adjusted the electronic load to basically suck this particular current, 100 milliamp, 200 milliamp, 500 milliamps, 1 amp, 2 amps, and I've even tried more than 2 amps, but over 2 amps problems arise. And in each case I measured, like I said, also the input current into the converter, and with the output voltmeter I have monitored how much the voltage drops, because pretty much every converter will have lower voltage with the increase of output current. So I wanted to see how much will this voltage drop, and these are the values. It basically, for this particular model, the voltage drops with 100 millivolts for every amp of current that the DC-DC converter outputs. Okay, and based on these values I have calculated the efficiency, which is just the ratio between the output power and the input power expressed in percentages. Okay, power being voltage multiplied by current. If I have 10 volts on the input and 5.05 starting voltage on the output, from which we are dropping a few tens or hundreds of millivolts, then it's a simple matter of you're just creating a simple formula that makes some multiplications, divisions, and additions in order to calculate this. And indeed the efficiency, the maximum efficiency, is about 90%, which is nice and is correct with respect to what we were told. Also, this high efficiency appears between 500 milliamps and 1 amp of current on the output. Anything less than that will have a smaller efficiency. Anything higher than 1 amp will also have a smaller efficiency, as we can see on the graph. But it doesn't vary all that much. Like, the lowest efficiency is about 83%, which is still pretty good. Okay, so nothing to comment about that. Regarding the ripple voltage, it's also pretty good, pretty decent. Maybe I shouldn't say good, but it's decent. It's not quite 30 millivolts as we were told, but it's close and it's not a problem. So when the converter does not have any load whatsoever, this is the ripple voltage. Okay, we have 10 millivolts per division. We have about 50 millivolts peak to peak of ripple. Not that big of a deal. When we are drawing 500 milliamps, the ripple increases a little bit, but not by much. We have about 62 millivolts. We have some very short spikes here and there that happen, and actually these spikes are the one causing this apparent increase in ripple voltage. At 1 amp, the ripple is similar to the one at 500 milliamps, and then at 2 amps those narrow spikes get a bit wider, as we can see here. And I had to zoom out a little bit from 10 millivolts to 20 millivolts per division in order to better see those spikes. And we have an overall 112 in this particular moment millivolts of peak to peak from one of these spikes to the peak of one of these spikes to the bottom peak of that particular spike. But the sine waveform that represents the majority of the ripple still stays around 40-50 millivolts, so it's still pretty good. It's not that big of a deal. Okay, so a module with this power, with this IC, even if it's cheap, I would say can be used successfully. Okay, maybe I shouldn't, maybe I wouldn't draw 2 amps from it. At 2 amps, I've measured about 50 degrees Celsius the board temperature, which means that the actual components were hotter than that. Okay, because I've measured the temperature with a very cheap thermometer. So maybe I wouldn't use such a small module for 2 amps, but for 1 amp it's not a problem, or 1.5 amps it's not a problem. We will get maximum efficiency and things will be okay, so it is workable. However, moving on to the second DC-DC converter, the one with MP1584EN, I cannot say the same things, sadly, and I will show you why. Now, as far as these simple measurements are concerned, they are pretty much similar to the ones we saw earlier for this particular IC. And the efficiency is also pretty high. It drops lower than the previous model. At 2 amps we get about 76% efficiency, which is not all that good, but top efficiency about 92%. So yeah, as far as efficiency goes, it's still pretty good. Also, the maximum current seems to be 2 amps if you ignore the other problems. The dropout voltage also seems similar, not quite, but similar. But this is a completely, or well, maybe not completely, but mostly unusable DC-DC converter. And it is mostly unusable due to the ripple, which at some point gets to be way too high for us to work with it. So at no load, we have about 5 millivolts per division and about 20 millivolts peak to peak ripple voltage, which is fine, okay, not a problem. Weird things start to happen when we apply a very light load at only 8 milliamps. The ripple voltage has become a lot more triangular waveform, and it has gone up to almost 40 millivolts. It gets a little bit better if we draw a more serious current, like 100 milliamps. We see a peak of 33 millivolts if we take into consideration this particular spike, but otherwise we have some 22, 24 millivolts or something like that, which is not bad. However, as we increase the current, the ripple noise becomes worse and worse and worse until it gets to be just unusable. At half an amp, I have about 130 millivolts peak to peak, which is it's significant. Okay, at 1 amp and above 1 amp, things start to get crazy. In this particular moment, at 1 amp, I had 380 millivolts, but as I was increasing things a bit, and even before increasing the current, at 1 amp, this particular waveform has various momentary spikes that are frequent but short. I mean, they happen only once in a while. So if I activated the persistence on the display of the oscilloscope, I was able to see these much larger spikes happen from time to time. And if we take a look and we see that we have 200 millivolts per division, and we count 1, 2, 3, 4, 5, 6 divisions times 200 millivolts, that's 1.2 volts of ripple, which is just crazy. And things get even crazier than that. At 2 amps I have about 3 volts of ripple noise, which is, well, no longer noise and no longer ripple. It's downright just I don't know, an oscillation, or I don't know how to call it. It's completely unacceptable. Okay. Also, I have changed so like I said, I've tested in total 3 DC-DC converters of the same module, of the same model, just to make sure that the first one was not broken, and they all behave the same. At 1 amp, for example, in this particular case, I had only about 50 millivolts of ripple noise. With persistence, we see that the noise is kind of fluctuating quite a bit. At 1.2 amps, this is fluctuating even more and has reached about 60 millivolts. And at 1.3 amps, so only 100 milliamps more, we are getting the same 600 millivolts as before, or something like that, which is significant. And I was curious to see how this voltage actually looks like, so I've set the coupling of the oscilloscope channel to DC. I've moved the zero line down here so I can set 1 volt per vertical division, and instead of having a relatively straight line around here, around the line of 5 volts, I have this sinusoidal waveform that, yes, it is oscillating around 5 volts, but having a 600 millivolt peak-to-peak ripple is just too much, and it's completely unacceptable for many applications. Okay, so yeah, my conclusion is that these kinds of modules, if you see these kinds of modules, okay, DC-DC step-down converters, be careful about them. Don't trust them, test them before using them, and honestly, I would avoid buying them from the very beginning. Like, honestly, I would just try to find something that is a bit more expensive, but something that would inspire more confidence, because these are not really good. If you really have a module that uses MP1584, then you're most likely gonna have the results that I've just shown you, and you're gonna have an unusable, or mostly unusable, DC-DC converter. Okay. It's not completely impossible to use it, but you'll have to be able to set its voltage higher than what you need, and after the DC-DC converter, you'll have to use a linear power supply, a linear circuit that stabilizes the voltage to that which you need. Okay, because it's clear that this DC-DC converter cannot do that for you. So it is somewhat useful, but not quite that useful. Okay, so yeah, that's about it. I hope you now know how to test a DC-DC converter, or in general any power supply. you know, you just have to perform this test and to take these measurements and perform these calculations. I hope you now know that you should stay away from extremely cheap circuits on the market, and yeah, I hope it was useful to you. Thanks a lot for watching. Please consider liking and subscribing this video. I will be making more videos. I'm trying to come up with videos on a constant basis. Also, if you enjoy my work here, please consider subscribing on Patreon. Any financial help is a good help. I can, by having financial help to buy components faster, I can learn things faster, and therefore I can come here and make videos to teach you things faster, so that you don't have to waste as much time and energy testing things and learning things, because I am consuming that time and energy for you. So thanks a lot for watching, and I'll see you soon in the next video. Bye bye.